Hi guys, we're Group 30 and our project is training humanoid robot hand to rotate block using deep RL. The problem is robot hand is not as dexterous as human hand, so we want to train shadow dexterous hand to perform reliable blocks rotations like human. And this is a sample video from simulation environment. Yeah, for why this matters is mainly because achieving reliable control remains difficult due to complex dynamics, multiple degrees of freedom, precise object control requirements, and its applications are really meaningful. For example, general robotic manipulation.
Our task is to re-implement and enhance and establish reinforcement learning framework in a simulation environment. Hand manipulate block dance is a genetic robotic simulation environment using multiple physics engine to simulate interactions between a robotic hand and a block. We implement an actor-critic connector to do the reinforcement learning. Each simulation step represents an 80-millisecond actor actions in real world. The environment returns an observation dictionary, including kinetic data for the block and finger joints, and the current and target block orientation in quaternion form. Each dimension in action space controls the robotic hand joints action. The default reward is the negative sum of the Euclidean distance to the block target and the angular difference to its target orientation. Our reward to the model is the difference between the current and previous time step rewards. The table on the right lists input values to the policy and value networks. The policy uses noisy input, while the value network receives clearer, more detailed information, resulting in an asymmetric actor-critic network.
Okay, we are using proximal policy optimization algorithm for our baseline model. And we are also use the policy network and the value network in our model. For the policy network is meaning to predict the probability of each action. And for the value network is to evaluate the action we picked by predict the future expected reward. And for our training pipeline, we are going to set up a bunch of interactive environment. And because we are going to train the model by a sequence of interaction outcomes, we need to build up a memory buffer block to connect the sequence of outcomes under the current policy and temporarily save into the memory buffer. Then send the sequence of interaction outcomes to update both the policy and value network for the next interaction round.
Yeah, and this is a result of our baseline model. And you can see, although the performance is not very good because of the limit of time and computing resource, and it's actually learning something slowly.
So yeah, let's talk about our model, which is RSAC, which is nothing but an extension of soft actor-critic network, and it uses LSTM layers in the actor and the critic network. So I'll just talk about the key features. First is the actor-critic framework, where the actor learns a stochastic policy and thus maintains a balance between exploration and exploitation. Second is the critic, which estimates the Q value for the actor's action. Next is in order to have randomness, we have the entropy regularization. And in order to maintain memory, we have the replay buffer that stores the state, action, reward, and the next state for the off-policy learning. And last is the LSTM integration, where the actor and the critic network includes LSTM layers in order to handle long sequential data and thus capture long-term dependencies. Next slide. So I used soft Q laws instead of PPO laws because it stabilizes learning by leveraging the target critic network, and it encourages the critic network to predict accurate Q values, and thus it maintains balance reward maximization with entropy-driven exploration. And talking about advantage of this loss is that it reduces variance by using a target network, and it also handles stochastic policy and entropy regularization. Next slide. So these are the results. Like the right side is the model. As you can see, the average reward keeps on increasing steadily as compared to the baseline model. So our model is like performing decent enough. Next slide. So conclusion is like a model is trying to learn an optimal policy as shown in the previous section, and it could get better with computation power. And future work includes running more ablation, different trying neural networks, and tuning hyperparameters. Thank you.